So now we're on to, Wayne, what was with the hat?
Oh, I was just trying something new.
I like new things, they're good. Okay, so now we're doing kinetic theories and kinetic models of a gas. First, Wayne, what is a model?
Well,
in
it's
physics.
something, and in maths, it's the same sort of thing.
Yeah.
It's something that aids us in explaining phenomenon and describing them. And we make a few assumptions. So it's normally an actual three-dimensional thing that we can look at and view from all angles and look at it. But if that's not possible, it's just a mathematical thing that we can use.
And you have assumptions that you set, certain things that can happen, and you make deductions on what will happen if this happens. And sort of
So in the kinetic theory model thing of gas, we have a box. I'm just going to draw a square with some gas in it.
There's a box, and as I said before, you make assumptions about what's happening in the box. So you have some of those.
We do. Firstly, we say that the volume of the particles is negligible to the volume of the container it's in.
We do. So the volume of the container is so much higher that the other one becomes almost insignificant. So I'm going to show that with
VC is volume of container.
And VP is the volume of particles. That's, yes.
These three greater than signs means so much greater than, and don't even be chatting otherwise, bruv.
That this one's like, well, silly.
Yeah.
Yeah.
So the volume of the particles is nothing compared to the volume of the container.
Then we have a few force things.
Yep, so gravity.
We're ignoring gravity because the particles are so small and they move so quickly that they aren't really affected.
Yep.
So we're going to say no gravity today.
Yep. Intermolecular forces,
So
like Van der Waals forces in chemistry, or
hydrogen bonds. We're pretty much ignoring them. We're saying that they don't interact unless they actually collide.
Exactly.
So that make it very complicated to take a lot of things into account. Then we can take into account the way they collide, so it's always elastic collisions.
An elastic collision always.
So that means that all kinetic energy is conserved, which is quite handy for some maths. And then finally we have that they're random, they're completely haphazard in their motion.
We're assuming the gas is what we think a gas is like. So it's random and it's haphazard. Now if there's a written communication mark, chances are haphazard or elastic would have to be spelt correctly.
Yeah, and that's quite an easy mark, so just learn how to spell them, that's fine.
I would always quote all 5 of these if possible.
Yeah, I would.
But it's only normally, it's never been 5 marks. I've said a 4 mark and a 3 mark version.
Yeah.
If you state all 5, you can't go wrong, can you?
Yeah, so there's that. Now we have our model and our assumptions. Let's see if we can deduce some things.
I read the first bit of the book before I got bored and thought, let's just film it.
Yeah.
So, and it said something about pressure. So
I've heard of that one.
yeah, there it is.
So we wrote this off. Well, let's remember our assumptions.
Yeah, we need to remember our assumptions.
So that's an important thing. So pressure, that's force over area, right?
It is. And if we think about it, we've got like a box going on, haven't we?
Yes, we have.
I'm going to attempt to draw a box here.
That's quite a little box, Wayne.
It's quite a little box. Hopefully you can see the box. But there's a box there.
There's a box, and this is our container containing our molecules. How many do they have, Wayne?
Well, I can sort of think of 3 scenarios. Inside the box, you can get a particle that goes up and down.
Yeah.
Like that. So it bounces from the top to the bottom. Obviously, in the real world, they collide off each other, but it's going up and down.
Okay.
You can have a particle going from side to side.
Just chill them to know that there's both of these going on.
And you can have them, this is a bit more awkward to draw, going in and out of the board.
Yeah,
it's easier in real life to say like that. Yeah. So there's 3 major motions. So they can go up and down, side to side, and in and out.
Okay, so we've got 3 molecules in our thing. So that's easy in ways, right? The force molecules over the area. Done.
Done. Easy video. But
force is a bit more awkward, isn't it?
It is. I mean, how would you work out the force?
I'm not sure. Let's think of what we have.
Okay. You have a particle and it's going to hit into that wall and it's going to bounce back this way. It's going to hit that wall.
That's alright then. That's alright.
I was going to bounce back this way. Oh. I had to duck an extra far because I had a
T-code in my head. Yeah, that's an issue. So when you hit things and you go back, there's momentum involved, isn't there?
And we have to remember our assumption that the collisions with the particles with the walls is completely elastic.
So not only is momentum conserved, which is always true, but all kinetic energy is also conserved.
It is. So the velocity will remain the same when it goes backwards. It will just be reverse velocity.
Yeah, so that means it's gone, as it's a vector, go that way, so it'll be 2mv.
2mv is the momentum, to change potentially a change momentum at 2mv, like that.
Yeah, it's a change of momentum because it's gone that way, minus one of them is 2. And Wayne, the change of momentum, that's force.
It is.
So the change of momentum is force, But the change in momentum is basically just momentum over time, right?
It is. So we've got this. Let's try and divide it by some sort of time if we can do that.
So we don't have time, do we? We want to get something else.
Yeah, but we can work out time with the easy equation, speed equals distance over time.
So if speed equals distance over time, then time is equal to distance over speed, or velocity.
D over V.
And so we can just substitute in.
We can, but when you think about it, it's going to collide with that wall, then it's going to bounce this way. It's going to hit that wall, and it's going to bounce back.
Okay.
So the distance is D, one side to the other, and then another D coming back. So it's 2D.
That's 2D, isn't it?
2D over V, that's the time.
Yeah. So if we divide our 2mv...
That's our momentum.
Yeah.
Divided by our time, we get 2mv divided by 2D over V.
Yeah, and that's the same as writing 2mv times v over 2d. And then we can sort them out because that's quite messy at the moment.
It is. For starters, these 2's cancel out.
Yeah, they do. Then we have our v's times together, that makes v squared.
So our force that's going on.
So our force is equal to
mv squared over d, and I like orange.
I like it's quite standoutish, isn't it? It's good.
It is. Yeah.
Yeah.
So F equals mv squared over d. That's nice.
That's handy.
We can do that. We know the mass of different particles.
But so you have the mass of one particle, right?
Yeah.
But we have lots of them.
We do. So let's say n, just to dictate the amount.
Okay.
Change.
So then I'll update this again, but I think I'll rub out a bit of this so you can sort of go in the middle.
Mhm.
So you rub out this bit here. So now we've made that. So now we have an F that we can now work with.
Equals
be
n mv squared over d.
Okay, now let's do stuff with this one.
Okay.
Right.
So firstly, we've got this n.
Mm-hmm.
But in this scenario, we've got 3 lots of n. Okay, because n can be any amount, but it can be going in any of these 3 situations.
Yeah.
So you could have 8 million going up and down, 8 million going from side to side, and 8 million going, which one have I not said, in and out.
Yeah. And they will, even if they're not going quite now, because they'll never go in just 3 perfect directions, but their overall will essentially be a sum of something in their directions.
Yeah. So we can say we've got 3 lots of n.
Yeah, so it becomes 3n mv squared over d, but I don't like 3n.
I don't like 3n, it's going to become awkward, I think. So we can just call that n and divide it by 3.
Yeah, okay. So,
we're just substituting it in to get n and dividing it by 3 to put it in place of this little n.
So that gives us 3d at the bottom there.
Now the reason it's because this is just simply rearranging. You might be sat there thinking, well, why is it good to have a 3 on the denominator but not on the numerator? And the reason we can do this is because this n, like we said, there's 3 lots of it. It's going for the number going in a particular plane, whereas this n takes into account all of them in all directions. And that's what we'd want to take into account when we work out the pressure.
Yeah. So now we've got our force, let's try and put it together with our area.
We could do that. But first, I found another way of simplifying what we've got here.
Another way?
Another way, even further.
Oh goodness.
We have n times m. Okay,
Right.
now m is the mass of an individual particle.
Right.
And n is the number of particles. So why don't we just call that big M for the total mass of particles?
Oh, that's a good idea.
It is. Let's do that. It just makes it a bit neater, doesn't it?
I'm writing this equation so many times.
Oh, but it's changing each time, and that's what counts.
That's what counts. So instead of just having, there we go, now we're just replacing that with one.
Yeah, one giant M. Yeah. Just to dictate the mass of all of it together, because that times out is going to give you the mass of all of them.
Okay, now we're good at the area.
Absolutely.
Okay, so our area is going to be d squared, because that's the distance we've gone for.
Yeah, so we've got a force divided by an area.
Yeah.
So dividing by an area is the same as dividing by 1 over meters squared, or d squared. And
times
dividing by 1 over d squared is
the same as timesing by d.
I've done that the wrong way around, isn't
Yeah.
it? Dividing by d squared is the same as timesing by 1 over d
There we
squared.
are.
Apologies,
So
that
should be a times sign there.
Trip myself up a bit there.
That's fine. So if we do that, then we have our pressure, not our force, because it's now quite different.
Yeah, because we've substituted into this. is mv squared over 3d cubed.
Yeah.
So that's our new equation.
So, but d cubed, that's just a volume, right?
It is, so we could just do
Change
3
that
lots
to
of the volume.
v.
And then what I did earlier actually turned out to be more useful than I saw at the time.
Yeah.
Because m divided by v is familiar, mass
It
over
is.
volume.
So it's like a p.
When it's been drunk,
And sort of
wobbling home.
Yeah. And then it falls into a
Oh,
boat,
like that, actually.
and it rose. Yeah, that's it. So if we then put that in, should I write on your side? 'Cause I'm getting quite low down on my board.
So the m over v is rho. So
Yeah.
what we're going to have is a third.
Yeah, so take the 3 out.
The m and v is going to cancel into a rho, so that's a rho, not a p. And then v squared is going to stay as it is. So it's a third rho v squared,
And that is pressure.
Pressure.
That was quite good, wasn't it?
yeah.
One change to make, by the way. One change.
One change.
Because our v squared, that's the average speed of the particles.
Yeah, because as we mentioned in a previous video,
Mhm.
the speed of each particle isn't going to be exactly the same at any point.
No. But we're going to change that because the real, this is sort of a simplified version, does more maths that you don't really see, but it changes v squared because it becomes the average of all molecules better than just the
It's
particles.
sort of like the root mean squared thing.
Yeah, it's sort of like a better, this is like a good estimator for c squared, isn't it?
Yeah.
Yeah.
So we could put p equals a third rho, and then it's denoted with a c with a dash on the top,
Yeah.
squared. And that's just the average sum of the velocities in a scenario.
Yeah.
But
So that's that.
either way work, because that in your exam, your v you'd be given would have been a pre-calculated average in a question.
Yeah.
So that would be okay.
So that's fine. And then when they ask you to calculate things, they'll ask you to calculate that. And then they'll ask for the squared one, so you don't square root it. And if they ask you to square root it, do that.
Yep.
Then that's that. That's quite a lot of...
It's quite a lot of maths. I
Yeah.
think the T cozy helped a lot.
So how did you... What do you think helped you most? What helped you think?
Well, in this scenario,
Yeah.
we used Newton's second law.
We did use Newton's second law.
And Newton, well, he likes apples.
He does like apples.
So I thought, why not be cosy with some tea and think with an apple?
That's a great idea. I'd give myself a tea cozy. Maybe an orange.